Hi everyone, Mr. Ford here again. Today we are going to continue with our optics packet. We are going to focus on spherical mirrors. Keep in mind with mirrors, light bounces off. Last time we looked at drawing our ray diagrams for the two types of lenses, convex and concave. We're going to do the same thing or very similar today as far as those three rules, but having mirrors, light is gonna bounce off of our surface. So here, just a picture. These again are the notes that are available to you on Schoology, just showing you why it's called a spherical mirror. It is a constant curve. So where this is where the mirror would actually be, it would continue that constant circle. This dot in the center, that's the center of our circle. This is going to be known as our center of curvature for our mirror. The other dot that I just circled here is going to be our focal point for that lens. You notice that it's halfway between the mirror at that point on that axis and the center of the mirror. So this is what it would look like just like before. We have our mirror, we have our focal point, this is our center of curvature, and we have our image, which was a candle just like last time. So we have those same three rays, parallel to focal, focal to parallel, and center. Some of them are going to change a little bit depending on whether it's a convex or concave mirror, and the center little rule is going to change a little bit. So again, we have light coming out of our candle, hitting the mirror, it would bounce off and go through that focal point. If we want to get really detailed and scale this, if we drew a tangent line here and looked at the normal line, our angle of incidence would be equal to our angle of reflection. And we can go and do that every time. That is the law, it still follows. This is just a little trick for drawing them so you don't have to perfectly line up a straight edge and a protractor. So it's still, we're following that same principle, or actually law, not principle. So we have our focal to our parallel to focal. Now our blue line here, we have our focal to parallel. Notice it's on the same side as the image because it is a mirror and light will not pass through a mirror. This is where it's a little different. So the center, it's not going through the center of our mirror, just like we used the center of our lens last time. It's actually going through that center of curvature. And something to note, there's no arrows on this. So if we really wanted to draw, light would come out of the flame, hit the mirror, and then bounce back and go the other direction. So if you notice, let's get rid of those. Let's do a color that's not on here. Let's go pink. Pink works. Right here is where all those three light rays converge. I forgot to erase one. So you see the blue, the green, and the red, all those three rays converge there, and that's where our image would form. So pretty easy to go through those three rays again. Our rules of if I do, I die, and hi ho die do, those two equations still apply. And we're going to do some practice with those. So if you scroll, or actually if I scroll, or if you take a look at your packet now, page 11, number 1. Again, those three rules are the same. Focal to parallel, parallel to focal, and center. We need to make one correction, though. Just with the answer key here, there's some inconsistency. So instead of changing the answer key, we're going to change. This was not actually the center of curvature of 2 centimeters. It was the focal length. So just so the answer key makes sense, this is an old packet that I'm working off of. It's a Mac pack. Things have changed throughout the years, so we want to keep the answer keys fairly consistent. So, and also keeping with the scales that we used before. If this was 2 centimeters, this mark here, this is 4 centimeters. So if we have a 1 centimeter tall object placed 5 centimeters in front of a concave, so we know we're on the left side because that's where the cave would be, we're going to be approximately, let's say about here is another 1 centimeter. Close enough. It's about 1 centimeter tall. Not too bad as I compare. So that's our object, and we're going to trace our light rays. So parallel to focal, 2 centimeters being our focal point. So we go parallel, best we can. We hit our mirror, and the light bounces off and goes through our focal point of 2 centimeters. The next one, focal to parallel. So we go through the focal point of 2 centimeters. When it hits the mirror, it will then reflect off and go parallel. Not too bad. And the last one, again, doesn't go through the center of the mirror, but through the center of curvature, which is the second other little dash. If you want to draw the fact that it goes out like this, that's fine. Not really needed. That it goes to the mirror and then bounces back. But that gives you a complete description of how the light's moving. And we see all three converge here. And it's upside down. So pretty good. So now we can go through our numbers here. The focal length, again, 2 centimeters. If we follow the 1 over focal length, 1 over object distance, plus the 1 over image distance, we plug all that in as 1 over 2 centimeters equals 1 over, let's see, object distance was 5. And our unknown variable, image distance. Plug that into a calculator, and we will get our 3.33 centimeters. The next part was our kind of more complex equation with the magnification equaling either the image height or the object over the object height, or the image distance and the object distance. Probably going to overflow to this next thing if I can't fit it all in. We don't know our image height, our 1 centimeter object height, and our 3.33 centimeter image distance. And our object was placed 5 centimeters away. Plug that in, solve for our image height, and we would get 0.67. You could argue that it was negative because it is on the underside of this. Again, we are missing a key component with this, is actually measuring it with rulers. So if this was our axis, it would be below our horizontal x-axis, making it negative, just for reference. And that would give us, if we could measure this a little bit, as far as magnification goes, 3.33 over 5 will give us 0.67, which, just because our object was 1 centimeter tall, it is the same as the magnification. Now, all the light does converge. We didn't draw any dotted lines. We are not on the other side of the mirror, so the light would actually focus in at this point. So it's going to be considered a real image. It was reduced, so our image height is smaller than our object height. and it is upside down or inverted. So that was how to draw a light diagram or ray diagram for a concave mirror. Now we're going to scroll down to the next page, I believe it was, or 2 pages from now, page 13. And this is a diverging mirror. So the last mirror focused all the light into a point. This one's going to spread it out. Now, if you remember from the diverging lens, it made a virtual image, meaning the light did not actually come together. So we got to keep that in mind here. So the scale 1 centimeter tall object, place 2 centimeters in front with a focal length of -2 centimeters. Now the -2, don't really need to discuss that right now, but what it is actually meaning is the light is not actually going to focus, so it actually appears to focus on the other side of the mirror. So that's going to change how we draw our light rays a little bit. So keeping in mind it is a mirror, so when you look in mirrors, you don't actually see, or I'm sorry, the image appears to come from behind the mirror, where we know that the light is not actually converging there. So this is a little bit trickier, and this is why I liked doing the lenses first as opposed to the mirrors. So we are a 1 centimeter tall object, 2 centimeters in front. So this is 2 centimeters. If we follow the scale, put this in here, and maybe a little big, but not too bad. Okay, so that's our image, or I'm sorry, our object. So same rules. We're going to go parallel to focal. So how it's a little different, though. Actually, should we... Oh, we'll do it on this one. You can look at the notes and see how it actually is a little different from the concave lens. But I'm just going to go through here. So it's going to go parallel, so parallel to focal. So it's not actually going to go this way, because that wouldn't follow the law of reflection. It's actually going to go up in this general direction. So it's parallel to focal, meaning it appears to come from the focal point. Remember, this is a diverging lens, so it actually needs to spread the light out. But I'm going to cheat a little bit, so you might not want to draw this yet, because I can kind of cheat since I have the iPad. But the dotted line represents where the light appears to come from. So it's appearing to come from the focal point on the other side of our mirror, hence the -2 centimeter focal length. So this is our parallel to our lens, or sorry, our mirror, and then appearing to come from the focal. The next one is our focal to parallel. Again, it's going to appear to come from the focal point. So we need to do a little... So this is where straight edge would come. So we could see on the mirror where this light would appear to come from if it was a straight line from that focal point on the right side. So I'm just going to estimate that's where it would hit the curved mirror and then go out parallel. That's good enough. So you can see it is spreading the light now. And the center is the same rule. It's appearing to come from that center of curvature. Sorry, my arm slipped. So it's appearing to come from here. So I'm going to cheat again and say it's here. And that light would continue this way. So depending upon how you want to draw it, is appearing to come from that line. Usually you can line a straight edge up and just have dotted lines coming, say, parallel from this one, and this would line up with center of curvature, but we definitely see where they all three converge right here, which is definitely a little smaller and upright. So the key is if you get three of the lines to converge, great. If not, something went wrong, or for our diverging lens or our diverging mirror, it's going to appear that the light is coming from somewhere on the other side of our lens or mirror. So let's see, so our focal length -2 centimeters, and that's just because it is not actually focusing, it's on the other side. We could still follow if I do, I die. So 1 over our -2 centimeters, 1 over our 2 centimeter location, object distance, plus 1 over our image distance. Use our calculator, plug that in, and we get an image distance of 1 centimeter. Then our magnification equaling hi-ho dido, where we don't know our image distance or image height, sorry. We know our object height was 1 centimeter. Our image distance, which we calculated, was 1 centimeter. And our object distance, which we were given 2 centimeters. So real quick math, we see our magnification is going to be 1/2. And simply because our object is 1 centimeter tall, our image height is going to be the same, 1/2 centimeter. So this is going to be a virtual image because the light does not actually converge. It appears to converge, appears to converge on the right side, but it doesn't. It is going to be smaller or reduced. So we can see that in our ray diagram and in our math that we did, and it was upright. So as soon as you complete drawing your ray diagrams and your calculations, please submit this to Schoology. Have a nice day.